There's one more big topic in chapter 1.3, and that's called the squeeze theorem. It's a general math idea that if you got something complicated that you don't want to deal with all at once, use a simpler version of it that's either always larger or always smaller, and then you can say something useful about the complicated thing, that it's always bigger than this or always smaller than that. Let's take this example, 7 times x squared times sine of 1 over x. This is an example. We're doing it as x goes to 0. Later in chapter 1, there are more interesting cases where x is going to infinity, and we have just sine x rather than sine of 1 over x. But for now, we'll just do it as x goes to 0 and sine 1, and have sine 1 over x. This is a limit of a product. Can we write that as the product of the limits? So can we say limit of a product equals the product of the limits? So then if that was true, we could say, what's the limit of 7? What's the limit of x squared? What's the limit of sine 1 over x? So limit of 7 times limit of x squared times limit of sine 1 over x. And again, if you don't write what the new x goes to is, it's just the same as it was before. That's the default. So what is the limit of 7? Well, how does 7 behave as x goes to 0? It's 7. What's the limit of x squared as x goes to 0? You know, for a polynomial, you can plug in whatever x is going to. So you get 0. And then what's the limit of sine 1 over x as x goes to 0? That's one we've looked at before. Remember, that one did not exist because it was oscillating without settling down. So we'll write what kind of a DNE it is. Oscillating without settling down. So do we have that this limit is 7 times 0 times DNE? What is 7 times 0 times DNE? Well, 0 times anything is 0, some people say, and other people say DNE times anything is DNE. Which one of those works here? Well, remember, the limit of a product is only the products of the limits if all the limits exist, and here we have one that doesn't exist. So we can't stop here. We can't just use this rule because this rule doesn't apply. So we can't use the product of limits approach. So what can we do? Well, graphing is not a bad idea. So sine of 1 over x does oscillate more and more as we get toward x equals 0 from both sides. But the amplitude is decreasing like a parabola as you go towards 0. So it's starting out with a large amplitude and getting faster and faster, but with a smaller and smaller amplitude. And the same thing is happening on this side. So what does it look like? You could graph this in Desmos. You'll see basically the same thing. So what does this look like the limit is? As x goes to 0, can you define a tolerance for any tolerance band of y around 0? Can you say you have to be at least this close in terms of x? Yeah, it looks like that's going to work. So it looks like the limit should be 0. And then the question is, can we prove that the limit should be 0? Well, let's apply this general math idea of coming up with something simpler that's always larger or always smaller. It feels like a little bit of creativity sometimes, but it's actually not creative. It's more mechanical. So what can we say is always bigger than something involving our limit? Well, our limit has a sign. What can we say is always bigger or always smaller than sine? You could say -1 is less than or equal to sine of anything, right? Is less than or equal to 1. I think that's a fairly uncontroversial statement. but it doesn't look like our limit yet. So let's do things to this statement to make it look more like our limit. The thing we're taking the sign of is 1 over x, so we could say negative 1 is less than or equal to sine 1 over x, less than or equal to 1. Agreed so far? It still doesn't look like our limit with the 7 and the x squared, so let's multiply each part by 7x squared. Oh, sorry, this is negative 1 times 7x squared, 7x squared sine of 1 over x, and 1 times 7x squared. Everything's good there. We have no danger of dividing by 0. We might be multiplying by 0, but we're not dividing by 0 at least. Is it what we're asking about at this point? We're asking about limit of 7x squared sine 1 over x. I have the 7x squared sine 1 over x, but I don't have the limit yet. Well, if these three things are in this inequality, then the limit of this one has to be less than the limit of this one, has to be less than or equal to the limit of this one. So I can take the limit of each part. So I can say limit x goes to 0 of negative 1 times 7x squared less than or equal to limit 7x squared sine 1 over x less than or equal to limit 1 times 7x squared. So this is saying our complicated function here is above this curve and below that curve. So we can go draw those in. What is 1 times 7x squared? That's a parabola that looks like this. Pretend it went just on that peak there. So that's 7x squared. And this curve, and we'll draw it in green or something, is negative 7x squared. Pretend that's a nice parabola. And it's an important part here that these things have to touch in the middle to be much use for what we want to do. So our upper bound and lower bound hopefully will touch right at the middle. In this case, it would be at x equals 0. If we were taking the limit as x goes to 5, then hopefully they would touch at x equals 5. So now what can we say? What is the limit as x goes to 0 of this? Well, that's just a polynomial. This whole thing is 0, right? It's a polynomial. You can plug in 0, you get 0. I'm not going to do anything to this. I'm just going to copy it. And then this is again a polynomial. You can plug in the 0 and you get 0. So the original function we asked about, the original limit we asked about, is somewhere between 0 and 0. I wonder what it is. We have squeezed it between an upper bound and a lower bound. So the way we do squeeze theorem problems is we start with a general statement that's true. It's usually some kind of trig function thing. And then we take steps, step by step, to make it look more like the problem we started with. And then we apply a limit in the last step and then do the limit. And hopefully that squeezes it down between the upper and lower bound to just one possibility left. So we can say, so by the squeeze theorem, our original limit is equal to 0. Back up here, we said you can't use the rule limit of products as products of limits because that's only true when they all exist. Here we weren't sure, is 0 times dne equal to 0 or is 0 times dne equal to dne? In some sense we shouldn't even be asking because we can't use that rule, but in this case it turned out the answer was 0. But there are different kinds of dne that you could use in the same problem. like how about x 1 over x cubed, or just cube root of x or something like that, where you get a different answer even though it still looked like 7 times 0 times dne. So in this case it did end up being 0, but in other cases the same form, 0 times dne, would not end up being 0, which is why we can't use that, that rule here.